Welcome back, everyone, to Academy 180, where we discuss a brief topic for 180 seconds, so we're all just a little smarter by the end of the day. Today, we're talking about blood and heat. Well, that is the thermodynamics of biological plumbing. And what am I even talking about? Well, it is counter current circulation. Just some groundworks we got to go over. Heat dynamics, everyone's favorite. Heat, is a reminder, is just a reflection of how much energy particles have. And energy wants to go from high to low. Therefore, heat is going to go from high to low. So basically, this is what drives all thermodynamics. Here we can see we got two low energy particles and one high energy particle. Remember these? These are going to be used later on to kind of demonstrate. So as time goes on, they're going to come together and meet, and you're going to end up with three moderate energy particles because they're going to try and reach equilibrium. Now, why that matters is in the body, we're constantly trying to reach homeostasis, which is just a fancy word of trying to say the body wants to maintain just kind of the same temperature, the same pH, the same chemical balance. Because all our enzymes, what runs our body, they require this level of homeostasis. As you can imagine, heating your home during the winter or cooling it during the summer, it can get expensive very quickly. So the body wants to do whatever it can to save costs and keep the homeostasis without expending too much energy. So that's where counter current comes in. So here we can see a non-counter current system. What ends up happening is you have these high energy molecules going to the extremities. In exchange, you have low molecules coming back. You can imagine those low cold energy molecules have to be reheated. That's very expensive energetically. So if we move those just a little closer right here, as you can see, what ends up happening is we have them come to the center here. So since they're close to each other, they're going to exchange energy, and you're going to have two moderates, and then they're going to come to the extremities. As you can imagine, this moderate energy is a lot easier to reheat than the low energy that originally was there. So you're saving on energy there. In practice, what we end up seeing is a few different examples. Arctic foxes, they live in freezing environments, but they're able to maintain adequate core temperature. Their appendages and nose are cold, but their core remains warm because of their countercurrent warming. Elephants, on the other hand, live in much hotter environments, and they're a big mammal, which means they have a large internal core which produces lots of heat. So they actually are doing the opposite of their using countercurrent circulation to remain cool. So everything we saw in the past slides, just flip it. And instead, you're going to have hot extremities like their ears, which can act basically as cooling fans, while their inside remains cooler. So that's it for today. Your homework is to look up two major arteries in the human body, compare it to the veins, and just kind of see how far apart they are or how close they are, and try and kind of apply that to how our heating and cooling works. Well, that's it for today. I'll talk to you guys later. Have a great rest of your day.